Welcome everyone to Foresight's Molecular Machines Group. Thank you so much for joining. Wherever you are, I think we really have like lots of continents represented today. It's really wonderful to see. Before we hit it off with today's presentation, I do want to take 1 minute to let you guys know that we now have the page for the Designing Molecular Machines workshop on July 10 and 11 in San Francisco ready. Many of you are already on here in terms of presenters or in terms of participants. And it's basically just our way of bringing the community that meets virtually for these like pretty regular events together in person. And so if you want to take a look at who's coming, if you want to take a look at the program, there's still a bunch of time to apply. This is now a little over a month until we will meet in person. And, like Foresight's, I guess, molecular machines effort have usually been through these technical workshops. That's how many of you met. And that's how many of you also came to this virtual group. And so I just really want to invite you that we're like, as we're nearing, not really post-COVID, but at least like a little bit more of a world where we can meet again in person. And let's take the opportunity, because I think the most valuable long-term collaborations really come from these in-person meetings. There's an application form, in the how did you hear about this workshop, just say you're part of this group. We'll try our best to make it work. And yeah, we would really love to see many of you in person again this year. Okay, wonderful. Well, that's it from my side. Today, I want to welcome two really wonderful speakers, both of whom have been at our technical in-person workshops, I think more than once, probably more, I think some than I have been even before I came to Foresight. And so, yeah, really just want to welcome both of you. Thank you so much for joining. You came here on a nomination from Michelle Simmons, who was talking a lot about your work and really singing high praise. And so I also want to take this as, again, another opportunity that if people in this group would like to nominate a presenter, would like to nominate a topic to discuss that we find presenters for, this is ultimately a container that we hold for you guys to tell us, the types of research, the types of topics that you think deserve attention, that are a little bit undervalued in the current molecular machines landscape. And so, yeah, really welcome you to nominate other folks as well. And so today we will have a really, really wonderful presentation first from John Randall on why the world is finally ready for atomically precise manufacturing. We already have heard that it may take a crisis. So really, really pleased for you to be here. Thank you so much. You've done a few really fantastic presentations at our in-person meetings again. And yeah, I don't think I have to say much about Zyvex. I will share a lot about this in the chat though. And for now on, the stage is yours, and I'm ready for Q&A and for questions in the chat. So thank you so much for joining, Randall, and take it away.
All right, Allison, thank you so much. I'm going to start off by sharing my screen and explain why I believe the world is finally ready for atomically precise manufacturing, and indeed it takes a crisis. Let me first thank my sponsors, DARPA, Department of Energy, Army Research Office, and actually the Quantum Economic Development Consortium is not really a sponsor, but something that I'll come back to quantum as being part of the crisis. So now if I can just get the slides to advance.
You should be able to by either hitting the right arrow or by clicking with your cursor onto the slide.
Oh. You would think the right arrow would do it. There we go. So first I want to mention that manufacturing precision is really critical to human technological progress. And Google and I picked out 4 particular inventions, the wheel, ball bearing, steam engines, and computing machines. And as best we could determine, this is when the first prototypes actually showed up, the dates here on the left-hand side. But it takes, although these were all prototype, they made no economic or societal impact until, in some cases, more than 1,000 years later, where in the case of the wheel, the chariots first showed up about 1,000 years later. The case of ball bearings, it took almost 2,000 years for first bicycles and a lot of other things to get ball bearings. The steam engine took a little more than 1,500 years to produce first the precision required to make good enough seals to make first the Newcomb engine, then the Watt engine that started an industrial revolution. And it's been about, depending on exactly how you count, I think about 158 years between Babbage's difference engine and the IBM PC or Apple II, take your pick. So why has the acceptance of APM taken so long? I mean, Feynman came out with plenty of room at the bottom in 59, the engines of creation published in 86, Don Eigler spelled out IBM in 89, Zyvex Corp was founded in 97. In the face of mountains of evidence that the dramatic advantage of atomically precise manufacturing, the resources for enabling this technology are astoundingly small. I believe that situation is changing. It takes a crisis. I will give you 3 reasons why I think APM is getting serious attention. We'll get a lot more. First of all, solid state quantum technology absolutely needs atomically precise manufacturing. Then there's a lot of international technology competition around quantum and some other things. And finally, there's the looming crisis in technology. One of the major reasons for technology advancement. This all adds up to lots of funding, the CHIPS and Innovation Competitors Acts, or lots of funding available for disruptive technologies. I'm going to first touch on solid state quantum. It's not my first quantum rodeo. Back in the 80s and 90s, I spent a decade of my life trying to make quantum resonant. Myself and a fabulous team of other scientists and engineers made some quantum resonant tunneling devices that were spectacular devices on their own. But the quantum wells and the tunnel barriers, even made with epitaxy, we couldn't make them accurate enough to get reproducible enough control of the energy levels and the quantum tunneling rates to combine them into integrated circuits. To make a vast overstatement, classical digital devices are insensitive to fabrication variation, and quantum devices are extremely sensitive. We could plug some numbers into some equations about the energy states and the tunneling rates. I just want to get down to, if we use semiconductor technology, especially the lithography, we're going to see huge changes in these energy levels and tunneling rates, which make it very difficult to make quantum devices, even relatively simple ones, much less qubits. Shown graphically, I'm going to come back to HDL. You heard from Joe Lighting not too long ago, hydrogen depacification lithography. If we take the very best that semiconductor lithography has to offer, the $250 million a scanner, EUV scanner by ASML, we can make dot sizes there's a recent publication about 26 nanometer, but with a plus and minus 6.5% variation in size, which is fine for digital devices. If we plot the first and the second on an energy scale, quantum states, you get a third of a millivolt here, over a millivolt here, much, much tighter control of the energy levels if we can use something like hydrogen depacification lithography. So it's a crisis. We do not have manufacturing tools to make quantum devices. Zyvex Labs is trying to change that, but we're not there yet. On international competition, U.S. only produces about 12% of the world's ICs now. There's significant competition in quantum, in just normal digital electronics, for leadership in several technological areas internationally. But there's now, because of this international competition, more funding now for disruptive technologies than ever before. And we need to take advantage of this. It's a crisis. So let me go to the looming problem for advancing technology. And I'm going to go to Norio Taniguchi's chart. I'm showing here a subset of his data. Taniguchi coined the term nanotechnology, was a Japanese academic studying the semiconductor industry back in the 70s and 80s. And he decided it'd be a good idea to plot the bleeding edge of of manufacturing precision. And so he measured this and then extrapolated fairly accurately out to about present day. And the change in manufacturing precision has been about 100,000 times, 5 orders of magnitude, and has taken us in 1910 from horse-drawn carriages to space tourism, from manually operated telephone exchanges to everybody's got a GPS cell phone that with access to huge amounts of information, some of it useful. And the life expectancy in the US in 1910 was 50 years of age. It's now 80. Well, maybe not for this guy. But also Moore's law, which has benefited greatly more than anything else to get more chips. We've had to have improved manufacturing precision, but the payoff in processor performance has plateaued about a decade ago. And we've, to misquote Feynman, I know Joe Lighting said there's still plenty of room at the bottom, but I believe we've run out of room at the bottom. If we've advanced technology by this improving manufacturing precision, we're now down at the quantized level of matter. There's not another 5 orders of magnitude improved manufacturing precision. So we're going to have to do something else to replace this improved manufacturing precision to drive technology. It's a crisis. Now, I'm going to suggest, first of all, I'm going to suggest in general that there's a way. What are we going to do? Well, I think I humbly propose this plan. I think there's a way to pivot to the manufacturing focus to continue exponential improvement in capabilities and create a new exponential manufacturing trend. I'm actually going to propose a digital approach to manufacturing, to fabrication, first at the nanoscale and then scaling up to ever larger sizes, not only for information technology, but for a wide variety of products. So we're going to start off with very small but useful nanoscale products and then move up to larger scales. Now, let me define what I mean when I say digital APM. I mean the making and breaking of chemical bonds with the binary functions. Which chemical bonds are made or broken is controlled by some digital address grid, a spatial digital address grid. That could be a relative one, reference to some nearby point, or a global one over a larger region. But we need a digital address grid, and very importantly, error detection correction is absolutely required. It's the only reason our digital information technology works. And so that has to be developed as well. I think it's reasonable to point out the vast majority of our nanofabrication, certainly that stuff that's used in semiconductors, is analog fabrication. Litho, deposition, etching, CMP, all treats matter if it's infinitely divisible. We largely ignore and often do battle with the fact that matter is quantized. There are a few exceptions that are creeping in, atomic layer deposition and die-block copolymer lithography, that do at least take advantage of the size of atoms and molecules, but they are missing some of these other attributes that I think are really going to be required to start a new digital revolution. Now, why will digital be better than analog fabrication? For all of the same reasons, by and large, the digital IT is better than analog IT. Tolerance in operations, ability to do error detection and correction, reliability of the processes, and because of that reliability, the ability to create extremely complex and yet reliable systems. And we can borrow processes from digital IT. Let me mention a couple of them real quick. There's a process you could think of this actually as massively parallel mechanochemistry, but I'm going to think of it as just addition. If we can make some structures that are atomically precise, first at the nano scale, and we have two identical surfaces and we bring them together, it's going to form a single crystal. A beautiful work was done about 12 years ago, not with covalent, but with some gold nanowires by a group from Brown and NIST. And TEM brought 2 gold nanowires together, applied a little bit of pressure, and then everything they could to find that original boundary between the 2 crystals failed. These made a single crystal. And so I believe we can do addition without error accumulation. But I will go further and say that I believe we can do that with some defect tolerance. Let's assume I've got an area that's 100 by 100 surface where we've got dangling bonds, but let's say there's a couple of add atoms. Now, there's probably some missing vacancies, but let's just assume we have add atoms. I believe that those 10,000 covalent bonds, when we press things together, are going to either take the add atoms interstitial or shove them out to the boundary. So I believe that even though there's a few imperfections, we can still maintain that the value of the atomic precision, and we can do this again and again without collecting errors. Let me give you one other quick example. In digital information technology, if you want to send some digital data packet over a noisy communication channel, we send that data packet and some validation bits. If the validation bits don't have the correct relationship to the data packet, then there have been errors. We simply throw that away, or in a few cases, use the validation bits to correct the errors, which can be done, or just ask for a resend. They're bits, they're cheap. Well, what if we have a way to make an exact, build a nanoscale widget to an exact atomic structure specification. First of all, we don't even have to create any validation bits. We can measure a subset of its physical properties, its mass. If it's a few AMU off, there's been an error. It's electrical, mechanical, or optical resonance. If they're not consistent with the structural specification, we simply throw the widget away, maybe reprocess the material and make others. Furthermore, there's already plenty of atomically precise fabrication going on that I believe could be digitized. You're going to hear about some beautiful work from Sergei in terms of using a scanning transmission electron microscope to do atomically precise motion. And I think that this could be digitized. Rick Silver's doing some beautiful work, not yet think of it in a digital way. We're certainly thinking of it in a digital way. Michelle Simmons, who you heard from, is doing hydrogen depassivation lithography, but not yet conceiving of it in a digital way. But Bob Walco's absolutely doing digital stuff. He's popping off single hydrogen atoms to make dangling bonds. And as I'll point out in a minute, he's also shown that you can do error detection correction. So there's many other opportunities for digital APM other than the one that we're pursuing. There's selective atomic layer deposition, selective atomic layer epitaxy, selective atomic layer etching, mechanochemistry, the work that Sergei's doing. On the organic side, DNA origami, diblock copolymer, other programmable self-assembly approaches, a lot of other ways to go digital that I think if people, you don't have to, I think it just gets a lot easier if you think of these processes within a digital fashion. Now, finally, well, not finally quite yet, what I want to talk about is a way that I think this can come in and create this new industrial revolution. Note, I'm showing an extension, which is really just a reflection, but not on the same. I haven't even put a time scale out here, but we run this down. We can't make features any smaller. I'd like to make products larger. And over here, I have volumes in terms of cubic microns, cubic millimeters, cubic centimeters, and some time scale where we start off very small, we achieve absolute precision or atomic precision with some tolerance, and build up to larger and larger volumes, both in terms of numbers and physical volumes of products, not restricted to information processing. Now, this is going to have to happen in steps because we're going to have to go from atoms to nano to micro, micro to millimeter, or some comparable stages. This was pointed out beautifully by John May in launching his Atoms to Product DARPA program that we had a role in, where we'll get to biology in a second, but he just showed with a very simple model, whatever the size of your feedstock parts are, if you need to assemble them into a 2D or a 3D structure, and you have a very high assembly rate of, say, 10 kilohertz, to go up to something that, let's say, is a square millimeter, and you want to take it up to a square meter, well, you can do that in about 2 minutes. If you want to get up to 10 square meters, you've got to do, or 10 by 10, 100 square meters, 1,000, excuse me. It's going to take you quite a period of time. It gets even worse in 3 dimensions. To get up to 3 orders of magnitude, you're up about a day. To get up to 4 orders of magnitude, it's years. We should point out that biology works this way. We start off with atoms. We build some lipid molecules. Lipid molecules make lipid membranes. Lipid membranes make cells. Cells make organs. Organs make organisms, never jumping more than about 2 to 3 orders of magnitude from one subcomponent to the next. So here's another point that I want to make about an inverse Moore's law. Okay, the easy part of Moore's law was at the start. The hard part is here at the end. Well, this is inverse, so we're going to start with a hard part, the part where we have to make 3-dimensional atomically precise structures. But once we do that, the assembly processes, I believe, will happen way, way faster. So if we can get the initial process to get to phase 2, scaling this will be much faster, and we can see the wonders of atomically precise manufacturing happen all that much sooner. And with the significant investment, we can push this disruptive technology into a phase 2 faster and rapidly explore these wonders. So now I've given you a vision, but what do I want to do? What I really want to do is share with you what I think we can get to at Zyvex Labs. We've picked a particular approach, hydrogen depassivation lithography. You heard Joe Lighting speak about this. It's a funny version of E-beam lithography, but it's way, way more precise. It's much, much higher resolution. I don't have time to go into the reason why this point spread function pushes an exposure zone for E-beam lithography out to about 4 nanometer radius, and produces a lot of partial exposure versus hydrogen depassivation lithography, because of a couple of nonlinear functions, produces an extremely small exposure zone, which lets people like Lighting and Walco pop off. And in fact, if we want to, we can pop off individual hydrogen atoms. We do so in a digital approach. We take as a pixel 4 surface silicon atoms, makes a sub-nanometer pixel. We can identify those pixels in our spatial address grid. A surface silicon 1002 by 1 reconstructed lattice is developed by Joe Lighting. And then we can run along a dimer row in a atomically precise mode, popping off both hydrogen atoms. If we're very careful, we can make absolutely perfect digital exposures where we remove exactly the number of hydrogen atoms we want to. Turns out we've got about a little over an angstrom, a plus or minus that, in tolerance, being away from the center of this zone. So we have some tolerance that we can work with. Now, Walco showed that you can actually, he's a proud Canadian, he was celebrating the sesquicentennial, made 150, and the particular maple leaf. And so he took away a hydrogen atom here. He didn't mean to. He missed a hydrogen atom here. He can both remove that hydrogen atom and actually fill a hydrogen atom back in, demonstrating complete detection and correction. So hydrogen depassivation lithography is digital lithography. With binary functions, making and breaking chemical bonds. We can do spatial digital regressing, and error detection correction. It's been demonstrated. We also are going to scale up through going massively parallel with MEMS-based scanners. We've already done a Z-axis scanner that scans at 10 times the rate while maintaining atomic precision. The piezo is still scanning, but the high response of the Z-axis allows us to do much, much faster scanning. We've done a study on this, says we ought to be able to put around 7 million STM scanners on a 300 millimeter wafer. There's already useful quantum devices being made. You heard from Michelle Simmons. I won't spend any time talking about that. The last thing I want to do, and I'm going to go a little bit over here, I apologize, but I want to show you a quick little explanation of how we think we can use hydrogen depassivation lithography to make 3-dimensional structures. And so we're going to show a fanciful, non-existent crystal lattice, but just for simplification, with unsatisfied covalent bonds that we're going to passivate with hydrogen atoms. We can look at those without disturbing the hydrogen atoms, or we can go in, raise the voltage and current, pop off those hydrogen atoms, then dose with a precursor, and this is what we don't have yet, well, gives us a full monolayer of atoms that self-limits, do lithography again, dose again, and repeat, and do that in 2 dimensions on the scanning, and then we can build up to 3-dimensional structures. We've already demonstrated we can do the silicon epitaxy, but now we haven't done it with atomic precision quite yet. My takeaways: there's a perfect storm of opportunity to realize APM. Digital atomic scale fab, I think, will be a second digital revolution, which, working with the inverse Moore's law, will be a new industrial revolution. Already some nice things have been accomplished. Now, there's many different paths to digital atomic scale and the inverse Moore's law. I presented simply one. Somebody please ask me during the Q&A about improvements that we've made to STM technology that are important in moving all this forward. There, I will stop sharing and turn the floor over to Sergei.
Wonderful. Thank you so much. We have already one question here in the chat, and that's, really just, we have many.
Maybe
we let Sergei go, and then we do the Q&A all at the end. Okay, wonderful. Yes, we'll wait until the end. Thanks, guys. Okay, next one up, we have Sergei. Sergei is a Foresight fellow, and Sergei will be speaking from the lab on the beam to the fab on the beam. So thank you so much for joining. Really excited to see Maxim also on there, who's also a Foresight fellow. So take it away, please, Sergei.
Thank you, Alison, and thank you, John, for the first half of the story. So basically what I would like to illustrate is a little bit more provocative and considerably less established direction for atomically precise manufacturing, which is related to using the electron microscope to actually observe and manipulate the matter. So this work was done over about 7 years by now by a large group of people at Oak Ridge, and now also includes our collaborators at the University of Tennessee and several other locations. First of all, what is electron microscope? So it's a very simple idea. You have a source of electrons. You have a rather complex electronics that allows you to compress the beam of the electrons into a very narrow subatomic probe. This probe goes through the sample, and then it goes through the detector. So the best way to envision how the electron microscope operates is imagine having a flashlight, having your hand, you shine the light on your hand, and then you see the shadow on the wall. So that's exactly what the electron microscope does. It creates the shadows of the atoms on the detector. The important thing is that in this case, the flashlight is incredibly small. So it is much smaller than the distance between the atoms. So if we raster the beam through the material, our shadow forms the pattern of the heavy and light atoms within the material. Depending on the setting, we can either look at the atoms themselves, or we can look at the deflected electrons. So there are some technical details and differences between the TM and STM. Another thing that we can do is we can measure the energy of the electrons that pass through the material. That's very interesting because electron loses the energy by interacting with the nuclei. It loses the energy by interacting with the valence electrons. It can lose energy interacting with the quasiparticles. And in this manner, we also learned the chemical and quasiparticle excitations inside the material. The thing that is really astounding is that the energy detection limit of the electron microscope now is 5 to 7 milli-electron volt, where the beam energy is of the order of 50 kilo electron volt. So this is absolutely amazing because you use the electron beam at tens of kilovolt energies to detect the quasiparticles, which are 5 milli-electron volt. It's not quite approaching the level of STM, but is getting very, very close. So traditionally, we think about the electron microscope as the machine that can visualize the structure of the solid. So these are a few examples of how the materials look under the electron microscope. So this is everyone's favorite two-dimensional materials doped by heavy atoms. Lo and behold, you can see these heavy atoms very clearly. If you add more heavy atoms, you start to see that they form some interesting patterns, some arrangements, so you can basically learn the material structure. But it's not only that. In fact, over the last 10 years, there was a veritable revolution in the field of electron microscopy with the near constant emergence of techniques such as high energy electron loss spectroscopy that I've shown, techniques such as the diffraction from subatomic volume, what is now called 4D STEM, and the emergence of the probes such as beam with the orbital momentum, when you can measure the orbital momentum or spin of the materials. And what's also very interesting is that this last 10 years of the development in the electron microscopy have been paralleled with the unprecedented growth of the deep learning techniques. And I will show you how these two techniques can naturally complement each other to make a sizable difference in how we can build matter on the atomic level. So this is all wonderful. We all know that electron microscope is fascinating. It can visualize the atomic structure. What does it have to do with the manufacturing? Let me show you an example. So this is what really happens when you put a sample under the electron microscope. So what you see here is molybdenum sulfide. So the bright dots are either molybdenum atom or 2 sulfur atoms. You can see a number of darker dots. This happens when you have 1 sulfur atom missing. So this is just 1 sulfur. Now look what happens if this material is kept under the electron beam. So all of a sudden, it doesn't want to remain the same. you can see that material clearly is unhappy under the electron beam. It falls apart because the electron beam removes sulfur atom. And from the perspective of the electron microscopy, this is really a bad thing. This is called electron beam damage, and damage clearly has a very negative connotation. But let's look at it from different perspective. So if you look at it from the point of view of solid state electrochemistry, what you see here is effectively a reduction of the material and a real consequence process of the phase transformation. You form single point defects, they aggregate into the extended defects, then you have the nucleation of the new phase. Excellent. However, if you look at it as a physicist, you can say, look, I have a collection of atoms, maybe I can recover the force distance field. But if you look at it as John or myself, as a nanotechnologist, you start to ask yourself a question. Look, I'm removing atoms of sulfur in a random fashion. But what if I tell my microscope to remove only the atoms that I want one by one? What if I know somehow how to remove the atoms in such a way that the remaining atoms self-assemble in the structure that I want? Or a next jump in the structure with the properties that I want. Can we do that? So we asked ourselves this question about 7 years ago by now. And the first thing that was obvious is that we really have to take the electron microscope and make it into something that it was not designed to do. So first of all, we need to understand how to control the beam. This is common in the field of STM. A lot of STM machines are home built. Electron microscopes are closed too. You're not supposed to touch it, they're under the service contract. You need to understand the beam-induced phenomena. You need to invest a lot of time into the dynamic range of the system because we use the same beam to modify material and observe the material. So we want to spread these processes in time. And we need to have some form of feedback. So if you notice that this part is very resembling about the self-correction that John made, yeah, that's true. That's because exactly what it is. So we spent a lot of time with John over beer discussing how to make this happen, and a lot of his ideas went into and insights went into making it happen. But then goes the second part. Vision is great, but it's all about the engineering in the end. And engineering here starts with the point, how do I take a data stream from the electron microscope and convert it into the atomic position and coordinates? So this is where the machine learning comes into play. So we started to work with the deep learning in the year 2016, so just 4 years after it appeared. And it took us relatively short time, about half a year, to take the data stream coming from the microscope and use the deep convolutional network to convert this into something like this. So this is a hole, there is nothing here. This is graphene, you can barely see carbon atoms, and the bright dots are silicon atoms. And now you can see how this image looks after it went through the network and atoms identified. Interestingly, it took us about 5 years to learn how to make this type of networks to run on the real microscope. So what you see here is the example of the microscope collecting data and the neural network that converts the data coming from the detector into the atomic coordinates in real time. Why is it difficult? It is difficult for the same reason why we don't have automated cars, despite the promises from Uber and Elon Musk by the year of 2017 or so. It is much more difficult than it sounds because there is a thing called the observational biases and the out of distribution drift. The car or camera or the microscopes have always slightly different setting. The network that is optimized for specific setting will not work if the setting changes a little bit. So there are ways to solve it, but it's longer than expected. Automated cars take time, automated microscopes take time. The second question can you ask is, can we use the microscope to make something? So what about phenomena? What can we do with the material other than blow holes in it? And it turns out that if we explore the history of electron microscopy, it is basically full with examples of people observing really phenomena induced by the electron beam on the atomic level. So this is the example of the crystallization. So this is a crystalline strontium titanate. You can see perfect lattice. This is amorphous strontium titanate. It's dark. It turns out that if we scan electron beam across this interface, we start to crystallize atomic light, strontium titanate to form the crystallite protrusion. So this is almost the solid state epitaxy. And it turns out that this process is controllable enough that if we tell our microscope to scan across the letters ORNL, we'll form these letters. And if we zoom in on it, you can see atomic resolution. So it's almost like a 3D printing in 2D. So not as John showed in the 3D. It's a 2D 3D printing, but it is 2D printing with the atomic resolution on the atomic scale. Question becomes, can you make it automated? And that was our first foray into the automated experiment, very primitive form long time ago, when we said that, look, we can scan the material, and we can make a very simple feedback circuit that detects the crystallization within the amorphous layer, and it tells the microscope to advance to the next position to induce crystallization once the crystallization event is detected. So this is how it works. So this is the microscope which automatically creates the strontium titanate patterns, so switching between the imaging and crystallization mode. And this is the end result. So it is possible to write the lines about 16 units cell wide and see that there is atomic resolution. This is strontium titanate. Of course, there is a silicon value. There is no strontium titanate value, but it turns out the same approach works with the silicon. So this is crystalline silicon, this is amorphous silicon, and this is the rectangular feature that was created by the electron beam inside the silicon. So the problem is, of course, that the national labs pursue only fundamental research, so it is theoretically possible to etch it out, but that requires a little bit different type of operation. But what we learned at that time is that not only we can crystallize silicon, but somehow we can also make this white marker atoms move around. So you can see that some of them moved. And in this case, if we scan electron beam, you can see that we have created a front of these dopants inside the three-dimensional material. And now we are talking about something which is really unusual. In this case, we are not controlling the atom on the surface. We are controlling the atom inside the bulk. Very thin bulk, 50 nanometers, but still bulk. That was interesting, but then we decided that rather than exploring the 3D, we really need to focus on being able to control atom one at a time. And to do that, we switched to the two-dimensional materials. And these are the few examples of how the process can go. So here you see the perfect graphene. Here we use the electron beam to create the hole, just vacancies. And now we have agitated this contaminant on the surface, which contains silicon atom. And one silicon atom has diffused and dropped into the vacancy on the graphene surface. So it formed a silicon insertion. So we manipulated the silicon to make a dopant inside the graphene lattice. It turns out that we don't have to even rely on the random process. It turns out that the electron beam can be used to manipulate atom and simply make it jump to the adjacent location. So this is how it looks in the real experiment when the beam makes atom jump. And if you're sufficiently patient, you can make the atom to go in the circles. You can make an atom go along the straight line, or at least the line which is straight for the government work. So the problem here is that this is done manually. And it took a lot of time and a lot of attempts because sometimes atom is kicked out from the surface. Sometimes the atom doesn't go where you want to be, but it is possible. And if it is possible to move atom, then it is also possible to move two atoms together and form a dimer, form a trimer, form a tetramer, make the tetramer rotate. So it is possible, but the problem is that for the time being, it is done by a human. It takes forever, and it's not very reliable. The microscope can operate about 1,000 times faster than the human can respond, which basically makes you think that maybe we need to be able to tell machine learning algorithm to control the microscope rather than do it manually. Of course, while these algorithms are being developed, as I mentioned, it's a little bit more complicated. We can experiment with making more complex assemblies. So it's possible to, for example, make molecules that comprise of different atoms, like titanium and silicon, platinum and silicon, iron and silicon, and so on. Then we asked ourselves the question that maybe we need to go back and learn how to create structures with the required properties and start with the materials that don't fall apart under the electron beam. So we deal with something solid. The great way to do it is something like nanoparticles. So this is a next generation of technique when we have the feedback from the image to the microscope. So you can see that we wrote ORNL. You can do it on the atomic level. So this is a nanocube, and you can see how we're creating a holes with the essentially the atomic precision. And in the end, it of course fall apart, but it's possible. And then we started to explore the evolution of the plasmonic properties. So plasmons are awesome because that's how you can connect the macroscopic world of light and that we can control to the atomic world of the plasmonic phenomena. That's how we connect quantum and macroscopic. And it turns out that if we drill these cubes, we can actually study how their plasmonic properties change. Now the final question. So we are clearly not done yet. We clearly are building individual bricks or individual supports on which the whole building of the atomically precise manufacturing in the electron microscope can be built. But the interesting question that remains is, can we use the microscope to discover interesting physical behaviors, right? Making the structure that we want is an important step, but we almost never know how to create the structure that has the properties that we need. It's a very different problem. So it turns out that the thing that we have been focusing on the last year was to teach the microscope to discover the physics that we're interested in. Not yet create the object with the physical properties that we want. Discover the physics that's already there. And this is the example of the microscope which is working automatically in order to discover the edge plasmon. So basically plasmon is the material taking the energy from the electron beam. The edge plasmon is a different type of the excitation that has a lower energy. So we told the microscope to automatically explore the material to find the regions which have the low energy plasmons. And what you see here is that there is a flake of the material. This is what is called the acquisition function. This is how machine learning decides what is interesting. And you can see that our microscope in the automated mode found the edges of the particle where the plasmons are. So we are slowly building this library of the capabilities. And now the process is going to accelerate by a big margin. So the microscopes are now having Python interfaces. So it doesn't require 3 people with experience in electrical engineering, microscopy to get together. Now, if this is something that you're interested in, drop me a note and we can do that. So if you run the Python code, we can make the connection to the microscope so that the Python code will operate over the real microscope. But generally, I think that this is a very exciting time. So electron beam manipulation is not nowhere as close to maturity as STM. There are very few groups active in this region. So the Oak Ridge, Vienna, and there are new efforts being developed in England and Singapore. However, electron microscope has these building blocks that satisfies those criteria that John have illustrated for ATM. It allows to visualize the solid on the atomic level. It allows to do it very, very fast on the time scale of milliseconds. It allows for correction. If something goes wrong, sometimes we can fix it. The only problem is that we don't control it very well. Humans are not fast enough to do that. However, this is why I'm very optimistic about the combination of machine learning and microscopy. And as I said, be a part of the future. Thank you.
Wonderful. Thank you so much. You have many hands up already. We're going to go one by one. Okay, this was quite the whirlwind. And we're starting with Ben first. Ben, if you want to unmute and ask your question. And yeah, let's see how many we get to. I'm sure that,
Okay.
there's many questions.
I'll do my first question, and then I have others that will wait till later. So I'm just interested. I've heard a bunch of everybody sort of points to the Atoms to Products DARPA program, but I've never seen it. It seems to have just like done some stuff and then ended. So I'd be just really interested in like sort of like what the ultimate outcomes were from that program.
Yeah, so there were some very nice results, but John Main decided after the first base section to concentrate on things on the more on the micro scale. So very little was done. We had the base period, but he didn't move us into the optional period, and he didn't move anybody, sort of working at the nanoscale into the optional period. So some very nice work was done on micro scale assembly and automating microscale things. There was some tissue making, people making tendons. I haven't followed how they've done commercially, but John, very apologetically, but he had a certain amount of money he had to work with, decided to concentrate primarily on the microscale assembly programs that he had.
And was that just sort of like a time scale sort of thing? Like the microscale programs were
Yeah, they were a lot closer to leading to in his opinion, a lot closer, and I have to agree with him, leading to commercial activities. And he wanted to show some out of a very aggressive program. He wanted to show some things that could make technological commercial impacts.
Understood. Thanks.
Wonderful, Alex.
If I may add, it is indeed the most important thing for atomically precise manufacturing is to find the customer for the minimal loving product. So we can make one device. By STM, we can make a device in for example, an hour. So we can project that the device can be made in about maybe 5 minutes. Why is it useful? In electron microscope, it is the same thing. We can manipulate atoms and come up with the specific atomic configurations. Not everything, but we have some basic science research can tell us what can be made, what cannot be made, and then it is try again, like playing Pac-Man. The question becomes, why is it useful? What problem does it solve for quantum computing, for quantum internet, for catalysis, for any of this field? If we understand the problem that we solve, then the field will blossom. If not, it will stagnate until we find a problem that we can solve.
It could be a really fun, maybe workshop discussion or just, general brainstorm in this group. Maybe we get a few people from other fields for that as well, and just doing that type of brainstorm.
I think that is exactly this connection that was a very strong motivation behind John and me being delighted to have this opportunity to talk, because the experience of the creative impact coming from Foresight community stays with us for a long, long time.
Well, it's all you guys.
There was a question that Ben asked that I totally buy the fact this could create qubits, which is incredibly useful, but I'd love some help seeing how 2D doped surfaces lead to a functional system. Ben, I guess you missed Michelle Simmons' talk. By doing hydrogen depassivation lithography, you can dose with phosphine, or now we found also with acceptors, and put dopant atoms in a single silicon 100 plane, do low temperature epi to bury that without moving those atoms out of that one plane. In addition to the single phosphorus atoms that Michelle, or she's looking also at sort of pairs of phosphorus atoms in some cases to make qubits. She can also make all the gates by just exposing slightly larger areas where she gets a quarter monolayer of phosphorus, which becomes metallic conducting silicon. So she makes all the leads that she needs to make, and does it all in 2D. Having said all of that, she's also exploring going in 3D. The biggest issue there is the epitaxial growth. Once you do, you like to work on this beautifully flat 2x1 reconstructed surface. The low temperature epi is required to keep the atoms in place, and it ends up with very good epi, but a rough growth surface. And so that leads to difficulties, not impossible if you want to just put gates as opposed to other single atoms. And people are working hard on that. But that's a very, in my mind, promising way to get to qubits. Not the only way, but a very good way.
Sure. I'm asking about something besides compute. Like what's something besides compute?
Actually, we've got a DOE program right now to make PN junctions. One of Michelle's former grad students or postdocs, Andreas Führer, showed that a PN junction of these delta dope materials is possible. We have a phase 2 DOE STTR working with Sandia for some modeling. We believe that some bipolar junction transistors will have outrageously high performance. They'll be rad hard as hell because they're a single monolayer buried well beneath any interface. They should work well at cryogenic temperatures and will have outrageously good control of their device properties, something that's extremely valuable in analog devices, which is what we're shooting for. There's
Isn't that low compute?
That's not for computing, but it will be great analog transistors put in the back plane of a digital computer. No matter what you make the computer out of, you need control signals, and the extreme high performance and the extreme control of the device properties that we believe we'll see, and we're very close to testing devices now, would be, and they work at cryogenic temperatures, or an excellent candidate for going as the analog devices in the back plane of any sort of quantum computer.
Let's see how many questions we can still do in the last 4 minutes. We have next one up here, Alex Lippert.
Hi, really inspiring talks. As a chemist, I like kind of a little bit of a focus on actually making the bonds. And in that regard, do we understand the nature of these dangling bonds? Are these silicon-centered radicals or some other type?
They're simply a unsatisfied covalent bond, and we primarily make use of them by doing selective deposition. By removing the hydrogen, you can get phosphine or boron trichloride to stick and put a dopant atom in place. But we've also shown you can do selective ALD. And so we've done titanium tetrachloride and water to make titanium dioxide. And working with S.V. Srinivasan, one of the founders of molecular imprints, we've shown he can use that to, at least proof of principle, he can use that to make a nano imprint mask. Now, it's not going to be absolutely atomically precise, but it's going to be way more precise than you can make with the best e-beam tools. And we think there's a lot of applications for that. We still have some scale up to do for most of those applications. But again, we have the other DOE support to make MEMS-based STMs and to make multiple. We're working hard to get 2 MEMS-based STMs to land on the same sample and both operate. Keep tuned.
Sounds very exciting.
Thanks, Alex. Next one up, Priyan.
Hi there. Yeah, these are really awesome presentations. I can't believe those movies and all that precision that y'all are getting. It's really wonderful to see after all these decades that this stuff is becoming real. Here's my question. We had the good fortune in this group in the past of having Lee Cronin come and speak to us about his computation. And in particular, I'm thinking of his language that he's created for expressing chemical synthesis steps using more traditional methods, his little robot reactors and all this. What I'm wondering is if you guys must need a language to control your microscopes, both when they're imaging and when they're manipulating. Do you think there's any possible benefit to combining or merging into his language so that you could actually, in some possible future, combine nanomanipulation with more traditional chemical synthesis, like prepare a surface and then have it go into one of his reactors with programmed reactions taking place? Maybe extend his liquid phase reaction stuff to vacuum phase stuff with chemical vapor deposition or whatever the appropriate technology would be. I see you nodding your head, John, so you're aware of his work. I'm wondering if
I haven't spoken with Lee in a while, but he does beautiful work. And let me point out, I haven't followed his sort of language creation, but this fits in beautifully to my idea of digital fabrication.
Right.
I think that language that he creates can become a programming language and can interface, regardless of what he might interface with us. I think he's going to lead towards a way of creating atomically precise structures by carefully programmed chemistry. But I do believe he's got to think about error detection and correction to really succeed in a grand way.
Yeah, I'm just encouraging you to reach out to him because I
will do so. It's a great suggestion.
But there was a way to incorporate nano manipulation type of reaction control with the more traditional liquid phase stuff then one could imagine automated systems that combine both environments to create more complicated stuff. Okay, anyway, thanks very much.
The magic here would be if we learn to do something equivalent to the biological PCR reaction, because we can scale both the electron beam and the STM-based fabrication much further than it can be now. But ultimately, there are still limits to how the sequential processing can work. Being able to use these techniques to create seeds and then use the solution chemistry to grow the seeds can make a huge difference.
Let me also suggest that if you haven't had him, try to get Chris Schaffmeister to come and talk about his spiroligomers. He's doing beautiful work in programmed self-assembly, creating 1D structures that then he deprotects a second binding site and has beautiful control over 3D structures. I started up a company. I talked to him a little while ago. If you haven't had him talk recently, you should really pull him in.
Thank you. Yeah, he'll be attending the workshop as well. We have 1 minute left, and I always try to ask the same question to everyone, which is, you can kind of decide. One is, what is the challenge that you'd like to see solved for your field to move forward? And the other one is, how can people help your work individually? Like, this is like a shameless plug moment where you can speak a little bit about what are you working on?
Real quick, putting dopant atoms exactly where you want them and making full monolayers in selective epitaxy. I need a really excellent surface chemist to help out. We have some great STM people. I'm a double E, but we don't we need some collaborators that are excellent surface chemists we can go a long ways with that.
Sergei, anything to add?
So for us, the primary challenge now is to make the connection to the machine learning world. So the Microscope of us, thanks to the manufacturers who build the Python plugins, we have done more in the last year than we did in 5 years before then. That's the perfect area for people who want to use the machine learning for atomic assembly to actually do it rather than just think or talk about it. And building this collaboration through the Foresight Institute sounds like exactly the right thing to do. Slightly more complex thing is we need to find a customer. So we need to find out what is our minimal lovable unit in terms of product, because assembly and machine learning we can do now with what we have. Scale it up and make this dream to come into reality is possible if there are people who think that this reality is useful. So it's not basic energy science. It's not the fundamental research. It's actually going to this proverbial value of death between the fundamental science and applied science, and finding out what technology and what customer allows us to make this first thin bridge over this value of death. That's what will make a difference.
Wonderful. Thank you.
The last thing I want to say real quickly is we've had great motion forward in working with Sergei and his group at Oak Ridge National Labs using machine learning for automating STM by doing STM image analysis with artificial intelligence and machine learning. So it's a great way of going.
Very cool. Hey, thank you both so much for joining. Really, really appreciate it. If you do want to propose, more of a brainstorming session, for actually getting some work done, we can always do that through Zoom. So thanks a lot for presenting here. And you've clearly blown some minds. I do want to remind people that if you're interested, apply to the workshop. And finally, also our Feynman Prize nominations are open. So please, 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 if you'd like to propose someone for the Feynman Prize this year, or for the Distinguished Student Award, then you can do so now. I shared the document in the form here in the chat. And yeah, please, let's help lift the amazing work that you guys are doing. Thank you so much for joining, everyone. It's now 3 minutes over time. And yeah, I really can't wait to see you guys for the next one. Bye, everyone.
Okay, thanks. Bye-bye.
Thank you.